friends. Today we are going to discuss about the MCQ question of chapter 13 Nuclei. Also the very easy numerical or the very easy MCQ question of this chapter, because the limited number of equation we are going to apply to solve the short numerical. Right? Okay. Now the first numerical is given. A radioactive element has the half-life of 6.3 years. Its original amount of mass is 1 gram. Find the fraction that will remain on decay after the 10th year. Now here the half-life is given. Tau half is 6.3 years. Now the initial mass of a given substance is given the 1 gram. So we have to find out the whatever the fraction is remaining after the total time is given 10 years. Therefore the half-life tau half is equal to 6.3 years. Initial mass m0 is equal to 1 gram. Time interval is given the 10 years. We have to find out the remaining mass. This data is given. Now we know the equation of the activity n is equal to n0 e⁻² minus lambda t, and also the equation of the tau half is equal to 0.693 upon lambda. We are using these two equations. First we find out the lambda, because from the equation of the activity m is equal to m0 e⁻² minus lambda t, or the I is equal to I0 e⁻² minus lambda t, we require the value of lambda. For that purpose we first find out the lambda. So we know that the tau half is equal to 0.693 upon lambda. Therefore lambda is equal to 0.693 upon tau half. Substitute the value of tau half. So 0.693 upon 6.3. So is equal to approximate 0.1 year inverse. Thus we obtain the radioactive constant or the decay constant lambda is equal to 0.1 year inverse. Now m is equal to m0 e⁻² minus lambda t. T is given, lambda already be found. m0 is also given 1 gram. So we substitute m0 e⁻² minus lambda is 0.1 into t is 10. Therefore m0 e⁻² minus 1 is equal to m. m0 is also 1. Therefore m is equal to 1 into 1 upon e. That means the 1 upon e. E is 2.718. Therefore m is equal to 1 upon 2.718. As we simplify it, we obtain 0.368 gram. That mass of the given substance is remaining after the 10th year. Again, radioactive element has the half-life 6.3 years. Its original amount of mass is given the 1 gram. That is the initial mass. Find the fraction that will remain on decay after the 10 years. What is the part of the given substance is not decay in 10 years? So from the equation of the activity I is equal to I0 e⁻² minus lambda t, or in terms of the number of nuclei n is equal to n0 e⁻² minus lambda t, or in terms of the mass m is equal to m0 e⁻² minus lambda t. Here lambda is required. So first our aim is to find out the lambda. So tau half is given half-life. So equation of the equation relate with the tau half, and lambda is tau half is equal to 0.693 upon lambda. Therefore lambda is equal to 0.693 upon tau half. Substitute the value. Actually here the value of the half-life is 6.93. 6.93. For simplicity, otherwise here the simplification is quite tough. Power of E. For that purpose, I take the here lambda value of tau half is 0.693. 6.93. So it becomes the 0.1 A inverse. Now equation m is equal to m0 is 2 minus lambda t. So power of the E becomes the -1 and m0 as it is. m0 is 1 gram, substituted here. 1 gram into 1 upon E is equal to 1 upon E. E is given 2.718. Therefore 1 upon 2.718, that means the 0.368 grams. Here. Okay. Now after that, the next numerical. The activity of 1 gram radium-226 is given 3.7 into 10 is to 10 becquerel. Right? Here the activity is given. Calculate the half-life. Avogadro number is given. Right? After that, the mass of 1 mole is m is equal to, atomic number is equal to 226 gram. Radium is given 226 gram. Clear? And tau half-life is given. We have to calculate the half-life. I is given as the 3.7 into 10 is to 10 becquerel. That means the disintegration per second. Disintegration per second. Now we know the equation m is equal to m0 E is 2 minus lambda t. Right? Or in other words, first we have to find out the number of nuclei in 1 mole radium, because we have to find out the activity of 1 gram. Activity given, we have to find out the half-life. For that purpose, the number of atoms in 226 gram is equal to Avogadro number. Therefore, in 1 gram radium, N is equal to what? So, N is equal to Na upon 226 gram. Na upon 226 gram. That is the N. Right? Now, activity I is equal to lambda N. We have to find out the half-life. But we know that tau half is equal to 0.693 upon lambda. Therefore, lambda is equal to 0.693 upon tau half. Substituted here. Therefore, activity I is equal to lambda 0.693 upon tau half into N. We require the tau half. Therefore, tau half is equal to 0.693 upon activity I into N. Activity I is given, N we found, so substitute the value. Therefore, tau half is equal to 0.693. Number of atoms, Avogadro number 6.02 into 10 is 223 upon 226 into activity. The activity is 3.7 into 10 is to 10. 10 is to 10. Thus we obtain 4.989 into 10 is to 10 second. That is the half-life of a given radioactive substance, radium. Again, the activity of 1 gram radium-226 is 3.7 into 10 is to 10 becquerel. Activity I. Calculate the half-life. We require the half-life T half. Right? Mass of 1 mole of radium is given as the atomic mass number 226 gram. We have to find out the activity of 1 gram. That means we have to find out the number of atoms in 1 gram radium. Therefore, number of atoms in 226 gram radium is equal to Avogadro number. Therefore, in 1 gram radium, number of atoms is equal to how much? Therefore, N is equal to Na upon 226. Now we know the equation of the activity I is equal to lambda n. Lambda not given. We have to find out the tau half. Therefore, tau half is equal to 0.693 upon lambda. Therefore, lambda is equal to 0.693 upon tau half. Substitute here. I is equal to 0.693 upon tau half into n. Now we substitute the value of n. Therefore, tau half. We calculate the tau half. Therefore, tau half here. Therefore, 0.693 n upon I. Substitute the value. 0.693 n is equal to, you get a number 6.02 into 10 is to 23, already given, upon 226. Now activity I 3.7 into 10 is to 10. So we obtain the tau half 4.989 into 10 is to 10 second. Clear it? Okay. Now the inverse numerical is also asked like to that way. Half-life of a radium-226 is given 4.98 into 10 is to 10 second. Find the activity of its 1 gram specimen. 1 gram specimen. Here the activity given, we find out, we calculate the half-life. Here the half-life given, we have to find out we have to calculate its activity. Both are inverse to each other. So our answer must be this. 3.7 into 10 is to 10 becquerel, that is the 1 QE. Right? So first we calculate the number of nuclei of the atom in 1 gram radium. Therefore, number of atom in 226 gram radium is in. Therefore, number of atom in 1 gram radium is equal to n. We have to find out n. Therefore, n is equal to Na upon 226. Na upon 226, that is our equation. We require the activity I is equal to lambda n. But lambda not given. Lambda is equal to 0.693 upon tau half. Substitute here. Therefore, 0.693 lambda 0.693 upon tau half into n. 0.693 into n upon tau half. Substitute the value. Therefore, activity I is equal to 0.693 and 6.02 into 10 is to 23 upon 226 of n. Now tau half is given 4.98 into 10 is to 10 second. So as we simplify, we obtain the activity is 3.7 into 10 is to 10. This integration per second. That means the becquerel. And 3.7 into 10 is to 10 becquerel. And that is known as the 1 QE. That is known as 1 QE. Therefore, the activity of 1 gram of radium is 1 QE if its half-life is 4.98 into 10 is to 10 second. So both numerical are inverse to each other. In this half-life given, we have to find out the activity of 1 gram radium. Here, for 1 gram radium, the activity is given, we have to calculate the half-life. Clear? Okay. Now next, the average radius of the nucleus is 6.6 FM, 6.6 FM. Therefore, I is given the 6.6 Fermi. That means the 6.6 into 10 is 2 minus 15 meter. The average mass of the nucleus M is given 1.0088 atomic mass unit. Find the average density of the nucleus. We have to find out the density U. And 1 atomic mass unit is also given 1.66 into 10 is 2 minus 27. Therefore, 1.0088 into 1.66 into 10 is 2 minus 27, that much kg, kilogram. 8. Okay. Now we are using this equation. R is equal to R0 is to 1/3. We require the density. Density is equal to mass upon volume. Right? Therefore, first we need to find out the mass. To find out the mass, here the atomic number is required. Therefore, A is to 1/3 is equal to R upon R0. R is given 6.6, R0 1.1 Fermi. That means the 6. Therefore, A is equal to 6 raised to 3. That means the 216. That is the 216. Now, density rho is equal to mass per volume. Now, total mass of a given substance for the nucleus is equal to mass of one atom, mass of the one nucleus into number of nuclei upon volume V. V is equal to 4 by 3 pi r cube. Right? Okay. Now, r cube, we substitute all the value. Already we found the r is already given. Therefore, m is 1.0088 into 10 into 1.66 into 10 is to minus 27. A 216 divided by 4 by 3 pi 3.1. R is given 6.6 into 10 is to minus 15 whole cube. Right? So, density is 3.17. 3 into 10 is to 17 kg per meter cube. That is the density of the nucleus. Again, how we find out the density of the given nucleus? Here the average radius and average mass of the nucleus are given. So density is equal to total mass upon volume. Total mass is equal to number of nuclei into mass of the one nuclei. So first our aim is to find out the atomic mass number that represents the number of nuclei. Therefore, R is equal to R0 raised to 1/3 is equal to A is to 1/3 is equal to 1 upon R upon R0. R is given 6.6 Fermi upon 1.1 Fermi, so only 6. So A is to 1/3 is equal to 6. Therefore, A is equal to 216. Number of nuclei is 216. Therefore, density is equal to total mass upon volume. Total mass m into A upon 4 by 3 pi r cube. Substitute the value, we obtain the density 3 into 10 is to 17 kg per meter cube. Right? Now next, if the mass number A increases, what is the physical quantity associated with nucleus remain constant? Mass number, that means the number of nuclei in a given substance increases. So which of the quantity is remain constant? So binding energy, density, volume, or the mass. For that purpose, we know that the density rho is equal to mass number upon capital M upon V. Capital M upon V. Therefore, atomic number upon 4 by 3 pi r cube. Rho is equal to, but I is equal to R0 is to 1/3. There is to 1/3. So substituted here. Therefore, density rho is equal to A upon 4 by 3 pi. Instead of the R, we can add down R0 is to 1/3 whole cube. So this simplification is A upon 4 by 3 pi R0 cube E. That is cancelled. That is cancelled. Therefore, rho is constant. Rho is constant. That is not depends on the increase in A, that means the atomic mass number. Again, the density rho is equal to mass upon volume. Mass is equal to mass is depends on the number of nuclei. Yes, the number of nuclei increases, so density is increased according to this. But average radius r is equal to r0 a is to 1/3. Substitute here. Therefore, density is equal to a upon 4 by 3 pi. Instead of the r, r0 a is to 1/3 whole cube. So a cancel. Therefore, rho is equal to 1 upon 4 by 3 pi r0 cube. R0 is the 1.1 Fermi, that is constant. Therefore, density is also constant. So density is remain constant with the nucleus. As the atomic mass number is increases. Now next, number of nuclei of radioactive substance are 1900 at time t is equal to 2 seconds. Then the number of nuclei at time t is equal to 4 seconds will be, right? So the remaining mass after the 2 seconds. Initially 1000, after 2 seconds 900. So what will be after the 4 seconds? Therefore, after the 2 seconds, that is the 900 into 100 upon 1000. That means the 90% mass is remaining. Therefore, the remaining nucleus after 4 seconds. After 4 seconds is 90% of 900. 19% of 900. Therefore, 900 into 90 upon 100. So it's equal to 810 nuclei. 810 nuclei will be remaining after the 4 seconds. First find out the how much fraction or the remaining mass after the 2 seconds. So initially 1000, after the 2 seconds 90. So 90, 900 upon 1000 into 100. So we obtain the 90% mass is still remaining. Now the remaining nuclei after the 4 seconds is in 90% of 900 are remaining. Therefore, the 810 nuclei are remaining after the 4 seconds. Clear it?